Hello. I welcome you to my talk with the title Climate and Relief-Induced Controls on the Temporal Variability of Denudation Rates in a Granitic Upland. Of course, this work is not done by myself alone. We are several people of several institutes who collaborated on the presented work. And again, thank you for inviting me. If you want to read up the publication, it's found in Earth Surface Processes and Landforms in 2019. Yes, my name is Gerald Raab, and I'm the lead investigator, and let's just start with the presentation. I have two parts. First part will be more an introduction to the research field, what we're focusing on, and the second part will be then the research results for this granitic upland we have investigated. So as the title says, we talk about denudation rates, thus surface erosion, soil erosion. And if you look here on a global map, we quickly see that especially mountainous areas experience highest rates. I work in Europe, thus Europe is main center of my research. What the main issue is with all these maps and data that we produce, they are only models based on very recent data, and we have actually a big lack of long-term data. And this lack is especially within soil erosion problems. And the main reason why we have so little information about soil erosion history, like over thousands of years, we mostly can cover just a few centuries. And I just quickly go over the conceptual idea of soil evolution so you better understand why we actually have this lack of long-term data. So when we start here with a conceptual soil evolution model from Johnson and Watson-Stegner, we have soil over time. In the beginning, of course, we have soil formation, so progressive perogenesis, where soil just forms and we have deepening. Generally, very simplified, we can say, okay, soil forms, so formation of soil is when the production is larger than the denudation. And for our sake, we just say, okay, denudation is more or less equal than erosion. Of course, you have weathering influences, but those are mostly minor. And especially in granitic uplands or so, where you have a very gentle rolling surface, you still can consider this more or less equal. At one point in time, of course, denudation can overtake production rates. That's a tipping point where we go to a regressive perogenesis and their profile becomes shallower. And this is mostly done through physical erosion, of course. Yet when we look then today, then in our profiles and we look what still remains from all this evolution, we only see this very, very small part, and this upper part, so this past evolutionary path is mostly lost. And we have little idea about past coverages, past sizes, past volumina. And therefore, just to state here that the capturing of these past variations, especially of surface denudation and soil erosion, remains very challenging on site. And there's a very simple reason. So when we look at the usual archives that we use to determine past surface denudation, past surface erosion rates, we use different sediment records like lake sediment records or the marine sedimentation rates or even speleothem growth rates. Yet all of these archives are catchment-wide approaches. And we use these catchment-wide approaches to describe what is going on in the backland, so in the denudational zone itself. And within the denudational zone, we have very little investigation techniques. Of course, we have like something like surveying or a couple of isotope methods. For example, here you can just put the stick in the ground, or even you can use bolts on rocks to determine some erosion rates. But of course, these still cover time span since the installations, thus maybe 100 years, 150 years, depends how early you started recording. And we actually have then here also a lack of methods to determine long-term surface denudation rates within the denudational zone. And this is where my research and our group focuses on, to determine, on the one hand, surface denudation data over longer time frames, so over multi-millennia. And on the other hand, to develop new methods that specifically target this research gap. So this finding denudation rates within the denudation zone itself. And we tested in this granitic upland I'm going to talk about a new approach. So we thought that tors, so large residual rocks that are still attached to the bedrock, might be a suitable archive that still have some information about past surface denudation rates. They can appear in a variety of shapes, of course. Here's another picture how they can look like in field. And we based our idea on their formation theory. So here from Migon and also from myself, we've done some drawings, and you can think like you start off with this fractured rock mass, then you have this weathering mantle. This weathering mantle, this saprolite, gets eroded away, and then the remaining parts, the more resilient rock material just remains, and these are then the tors that you would like to investigate. So a more easy illustrated evolution model, for example, if you imagine a popsicle ice cream and the tor underneath the saprolite, it just gets washed away as the ice gets also eaten away, of course. And when we quickly think that the ice color still tells us something about the past, we still can determine where which volume more or less was. And we thought that, okay, certain isotopes, especially isotopes in the rock surface, might be telling us also something about the past evolutionary path. And with isotopes, I predominantly mean cosmogenic nuclides. So for those of you who are not familiar with cosmogenic nuclides, I also give you a brief introduction here. So cosmogenic nuclides, they're just formed through the constant bombardment of cosmic rays. So these are high energy particles, and they cause spallation, as you can see here in the background. And this spallation not only occurs in the atmosphere, it also occurs within the rock surface, so more particular within the mineral assemblage. So if we look here at our minerals, for example, we take quartz, most common mineral, and as quartz is also built out of other elements, as we know, silicium, oxygen, also these elements can spallate in other isotopes like aluminium, beryllium, 14C, and so on. And because it happens within this mineral assemblage, it's called in situ. And they're, of course, trapped. They cannot get out. So they start to accumulate over time. And what we do is that we measure the content of certain isotope, and then we recalculate their surface exposure age. And for our research I present today, we predominantly focus on beryllium because it has the longest half-life, and it's a very reliable method currently. So coming then to our main hypothesis, we had here our tors again, which with the saprolite, they get stripped away, or the soil later on if it's converted. And then we can add our beryllium idea. And we thought, okay, beryllium, of course, the content should increase from bottom to top as the top is early exposed to this cosmic rays compared to the bottom. And therefore, we should also have increasing surface ages from bottom to top. And by measuring in several surface ages, we might be able to determine surface denudation. So after this short introduction, I come to our study area. This is a wonderful granitic upland in southern Italy. You see here this gentle rolling paleo surface. So more specifically in Calabria, so southern Italy, as I said, in the Sila Massif. It's tectonically stable, it has a more or less consistent lithology, there's no large material influx, no past glaciation, and so on. So it was perfect actually to test our main hypothesis. And we focused our sampling campaign here in the center of this massif. This is a relief of our a dam of our study area. And we investigated there 5 tors. Okay, so we investigated 5 tors to compare them and look at what we find. And the sampling procedure was very straightforward. So we took samples from top to bottom. And as I said before, we expected higher content on top older ages and lower content in young ages on the bottom. In addition to these tors, we also investigated a couple of boulders, so rocks which are not attached to the bedrock, and scarps. So just along hill slopes, the scarp that comes right out, to see if we get similar results or if they differ or not, and just to see how these different landscape features behave within an enclosed area. Very simply, we went to field, we took our rock samples, we did some target chemistry to get our beryllium, we measured it with AMS, and finally we got our beryllium content. So this is now the beryllium content of our 5 tores. On the left scale, on the Y scale, you see heights above ground, and on the X scale, you see the beryllium content. You quickly realize that we have found this nice increase of beryllium from bottom to top. For example, here at tor number 5, you beautifully see this nice trend, very straightforward. Also here, tor number 1. So we see that there is an increase, and this gave us also, of course, confidence that the surface ages should also increase. So let's take a look here at one of our tors. So this is tor number 2. These are the sampling sites, so they're the position where we have taken the rock samples. Of course, we excluded this part because it obviously has fallen off, chipped off, and it would have just given us a very, very young surface ages. And we converted our contents to surface ages. And we see again, we have this increase. Just as a reminder, surface ages are given in kilo years. So this Ka, this means 106,000 years, 98,000 years, 31,000 years, and so on. Of course, we can plot these ages very simply in an XY diagram. And as you can see here, and we applied for the age determinations also different rock erosion rates. So rates that say how much the rock itself, the surface that we sampled, has eroded over time, which of course changes the surface age that we will calculate, as you can see here for the oldest samples. The older the sample, the longer it has been exposed, the more impact this rock erosion will have. What we did then is we used exponential functions and also logistic functions of Lichter. And we did some Monte Carlo simulation of their different exhumation path. And we used then the first derivatives of these individual functions to get their soil erosion or surface lowering rates of the surroundings. So this is what we have done with the tors. This at least here for tor number 2. And we wonderfully see that we go back over 100,000 years. We have more or less a continuous timeline. We have done it in situ, so within this granitic landscape, not somewhere with a catchment. And we have seen tors. Okay, they look. It looks like it works. And we've taken then a look at our boulders. So when we look here at our boulders, first again you have here beryllium content and heights above ground. We see that they age, so the content is spread all over, and so are the ages. So these are just the ages of the sampled boulders, and we see that like older stages is on the bottom, younger ages are on top, or both very young ages are on top and bottom. So it's very unclear what actually happened. We have of course some ideas, but they obviously are not fit as an archive like the tors are. When we go into our scarps, we also see that the content is very close together. We have maybe here some trend here with scarp number 2, but the rest is all very close together. So here are the ages, for example. And when we look here, we see that all the surface ages are very, very young. So between 9 and up to 15,000. So they do not cover a long time span. Also, when we look, for example, at this scarp here in picture C, then we see that we go here from 9,000, okay, up to 12, maybe, okay, this peaked a little bit earlier, and then again 9. So this whole scarp, which is like 30, 40 meters long, has been exhumed more or less at the same time. The same goes here for scarp number 2. It's very close together with the ages, and obviously also not suitable as a long-term archive. So these are our ideas, for example, for the boulders. We just think, okay, maybe they has just toppled out, they have been moved otherwise as they are not attached anymore to the bedrock. As I said, for the scarps, they have been exhumed very, very rapidly and very, very recently. In contrast to our tors, which provide these long-term trends from 100,000 years to present and still allowed us to determine different surface erosion rates. So this brings me back now to our TOR model. So this was our TOR model, and as I stated before, we have now enabled a continuous surface denudation model up to the Pleistocene, which is really, really great. Yet the title states that we have found some climate and relief-induced controls, and this is because we found some very interesting extras with these TORs. So this is here a relief of our sampling site. So you see here was our sampling site. This is the line here, southwest to northeast. And this is the position of the individual TORs that we have investigated. And these are the individual models of each TOR. And on the bottom, you see now again XY scale of age versus surface denudation in millimeters per year. And we found that when we compare TORs of similar landscape positions, they behave similar. And over the next slides, I will just use the average rate, so these black lines, for easier comparison. So first of all, we divided, of course, this relief into different sections. When we look at the first sections, these are the slopes. The slopes have been exposed, and they had their highest peak very, very recently. It started around 25,000 years ago. When we think about the scarps, mostly between 15, so the scarps were down here. They were around 15 to 9,000, so they were somewhere here. It also fits if we go to a lower elevation. When we think then of our ridge top, the ridge top has more a continuous exhumation path in contrast to the slopes. And when we then go to the more planar surfaces, which were not that steep, we see that these have been exhumed at the same time as the slopes, yet with much lower surface denudation rates, which is also something you would expect, that you say, okay, steep slopes, higher surface rates, planar surfaces, lower surface rates. And this is something very, very unique, that we could capture the in situ topographic effect on surface denudation within the denudational zone. And this is something really, really unique of this approach. And we are really very proud of it. We compared it, of course, with catchment-wide derived rates of this area, which were available here from Olivetti from 2012. And our rates fit very, very well with his results. However, we can show the variation, not just the catchment-wide derived averages. And this is also important if you want to get then into more details about climate factors that may have influenced the exhumation and the surface denudation of this area, which I will come to it a little bit later. So just a reminder, if we look back at our gap here, this TOR exhumation approach, so this is how we called it, T. It sounds very British, but it's Swiss. This TOR exhumation approach actually allowed to unravel at least some part of this research gap already. And of course, we asked ourselves, how do our past rates compare to modern rates here with fallout radionuclides? And I'll just give you a very quick idea here. We started off here with this in situ temporalium-based models. It's a continuous model where we put all our models together. And these are the rates from the plutonium. We see that the recent rates of the last, so the plutonium covers around 60 years. So the last 60 years, they had a rise, and they're really, really high compared to these past long-term rates. And I also have to say that, of course, in this area here, we have a research gap still, as I also have shown in the previous slide. We have no data how this went from here to there, but we just ask ourselves, what was the timeline? What events occurred? Why do we have a bump here and a low here? And what were the reasons? And therefore, again, I come to our combined models, where you have now, again, the slopes, the plains, and the ridge models. And on the bottom, again, the age scale. And the first thing that we checked is, do our surface ages fit with other surface age estimations? And I did a study there 2017, together with some colleagues, of course, from Italy. And we have found some volcanic deposits from this period, from 80 to 90,000, nothing much older, and an average soil age of around 45,000 years, younger soil age estimates around 15,000 years, which fit again very well with our scarps, which were also around 15, and oldest age estimations around 60,000. So these were other age estimations that, okay, our model does not only fit with the catchment by derived rates, also the surface ages fit quite well with independent other studies. Good. The next thing that we looked at were climate and vegetation data. So we had different climate phases, of course, which are only approximated, as we're not so as precise there, as we don't have the very local data. It's a couple of kilometers away from Ellen et al. And we have again this warm humid phase, cool dry, warm dry, cool dry, and warm humid. And for the vegetation, we started off with a very dense forest, and we went over step Bs, and then again we came to a forest, and today it's actually changing to a mixed forest through anthropogenic influences. And we thought, okay, we have here the oldest volcanic deposits, and very probably the soils are very young there, so we should have progressive pedogenesis. But in order to determine if we had really a progressive pedogenesis, we have to know several factors. So we know, of course, surface denudation, but what about production of soil? And therefore, we looked at different soil masses and different surface ages of various publications for volcanic soils, andesite soils, Mediterranean soils, alpine sites, and so on. And we used then their correlations to determine their soil formation and production rates for particular surface ages. For example, when we say, okay, we have here now a soil which is today around 10,000 years old or 15,000 years old around, we have around a soil production rate of 100 tons per square kilometer a year. So what we did is we then just combined the different surface denudation rates up here with different production rates at different time steps. And we came up then with this kind of model where we said, okay, at this time we had this soil deepening, we had really soil formation, early genesis, high production rates, until we reached here balanced pedogenesis, which fits again very well with our average soil ages. The soil production was more or less equal to surface denudation, until we reached the tipping point somewhere around 15,000 years. And there the regressive pedogenesis kicked in, especially through physical erosion. And I want to point out that our long-term model suggests actually a drop, which might be the reason through this through the vegetation increase again. So when we have this change from step Bs to forest, first here there was strong change from a dry to more humid conditions, but with less coverage of vegetation, thus erosion increased. And then as the vegetation started to pick up and higher vegetation climbed or peaked, then the surface denudation, probably the long-term surface denudation also decreased again. However, we see that modern erosion rates for the last 60 years is quite high compared to all our models here. And we think that this has much likely an anthropogenic influence, especially through the chipping down of the forest for construction material in the past centuries. One thing I want to point out before I come to my conclusions is that although we had more or less similar conditions, warm, humid, and forest coverage, we have very opposite soil formation theories here. And the reason is quite simple. When we were very young, we had very high soil production rates and therefore high soil formation. And today the soils, of course, became older and their production rates just decreased. This brings me to my conclusions. So again, for our research gap, we have this TOR exhumation approach developed, which could cover now a certain part of this research gap, but there's still, of course, some remaining. In summary, TORs are a usable archive to determine surface denudation rates continuously over geological timescales and, of course, in situ, so within the denudational zone. I've also shown you some climate change impact, so Pleistocene Holocene transition, where we have this increase of surface denudation, which I've showed you before. I've also pointed out that this denser vegetation cover, of course, counteracted until human interactions, also contributed to lowering surface denudation rates. And of course, the most prominent aspect that we found is that this topography determined the extent of surface denudation in this upland. And therefore, I hope you enjoyed the talk. I thank you very much for your attention. And you have any questions beyond this webinar today, just go to my website. You can contact me there, and we can have a chat somewhere extra over Zoom as you wish. Thank you very much.
Okay, thank you very much, Dr.